All right, everyone, let's go ahead and get started. So today we're going to do a bit of a review on resonance. As I promised on Friday, we'll do some conjugated dynes. We're going to look at the stability of conjugated systems, and hopefully we'll have a little bit of time to go ahead and get started on the next section so that I don't have to worry too much about that when we have our inverted lecture on Wednesday. So we're going to kind of go through the resonance review fairly quickly, and then we'll get into the real meat of things, okay? So let's look at some examples. How could I draw a resonance structure for tin, for example? And move it where? Move it this way? Move it which way? Right here? And put the double bond between these two carbons? Okay. And where would the positive charge go then? That's right. It would go on this carbon right here. Okay, so we can draw resonance structures for this. Would this one be the major contributor or the one that we draw? And why? That's right. We'd have a tertiary carbocation. How about for 11? Can we draw resonance structures? What'd you say, Jamie? You said yeah? You're correct. How would I draw it? What would I move? I'd move the double bond to the oxygen and put a lone pair on that oxygen, right? Which would give a carbocation here. Which one of those would be the major contributor, the one that I drew or the one that we currently have up on the board? Not the one that I drew, and why not? Okay, but the one that I drew also has what? A carbocation, which, does it have an octet? Everything here has an octet, correct? Right, so keep that in mind. Remember that octet rule business. How about 12? Can I draw a resonance structure? What do you think, Blaine? Think I can draw a resonance structure? No, I cannot. Why can I not? That's right, I'd have to break or move atoms, right? So if I tried to move this double bond to here, I would actually have to move atoms to do that. So it's not our double bond, or double bond, single bond, charge kind of motif that we've been learning about, right? What could I do here? It wouldn't be a resonance structure, but what could I do? I could do a hydride shift, right? I could shift either one of these hydrogens or one of these hydrogens. Which ones would shift? That's right. If I shift this one, then I'd end up with an allylic cation. If I shifted these, I would just end up with another secondary carbocation. Okay? So I could do chemistry on that carbocation. I can't do resonance structures. How about 13? Gabby's shaking her head yes, she's correct. I can draw a resonance structure. How would I draw that resonance structure? Okay, I'd start from the oxygen lone pair and form a double bond, right? And which would be the major contributor? This one or the one that we would draw? The one that we would draw, because everything would have an octet. All right, very good. Let's skip that for the moment. How about 22 and 23? Let's look at 22. Can I draw resonance structures? Okay, Brian says yes. He's correct. How can I draw that resonance structure, Brian? This would go where? Okay, I know what you're trying to say, but let's think about how we say it, okay? We're not going to move this double bond here. That would violate the octet rule. But what can I do? I can move the lone pair here to form the double bond, and what happens to this double bond? Goes up, that's right. So how we think about that is important, right? And so which one of those would be the major contributor? Would they be equally contributing? They're equally contributing. That's exactly right. Okay. How about 23? Can I draw a resonance structure? What do you think, Carl? Mm-hmm.
To the, how would you say it, to the right?
Uh-huh, right here.
Yes, sir, and the oxygen, double bond would go back to
Right,
oxygen.
so we'd put a double bond here and a single bond to the oxygen, right?
Yes, sir.
Okay, this is known as an enolate. This particular thing will come into play an awful lot in upcoming chapters, okay? And so we would have a resonance contributor Which one would be the major contributor? This one or the one that's on the board? Why? Everything has an octet there as well. Pardon? The negative charge is on the oxygen, and that's better than being on the carbon because? That's right. So this is the major contributor to the overall resonance hybrid. However, in future chapters, when we start talking about enolates, 99% of all the chemistry occurs at carbon, not at oxygen. The carbon behaves as a better nucleophile than the oxygen. Can anybody tell me why? Why would a carbanion be a better nucleophile than an oxygen anion in this particular case?
Because the carbon doesn't want to be in the anion, and that's why it wants to have the.
You're close. Kind of dancing around it a little bit.
Because of that, it wants to give away its
Which wants to give away its
low pair.
low pair? Why?
If it only wants to have, or it only has 4 valence electrons.
It still does. Or has a valence of. What do you think? Okay, well, oxygen would like to have a valence of 2 too, right? Why would carbon be a better nucleophile than oxygen? Okay, you're on the right track. You and Matt are both on the right track, but why? What's the difference between an oxygen atom and a carbon atom? But tell me the one that matters, though. Electronegativity. That's exactly right. So oxygen is doing what to those electrons? Holding onto them more tightly or less tightly? More tightly. What about carbon? Less tightly. And if it's holding onto those electrons less tightly, so to speak, is it going to be more willing to share them with something else and react? Yes. Right? And so the carbon atom, even though it is this negative charge being on the carbon atom is the minor contributor to the resonance hybrid, it still is going to count for most of the chemistry that we learn about with enolates. Okay? And so it's important that you remember that just because we have a minor contributor to the overall resonance hybrid does not mean it's insignificant. Okay? So keep those things in mind. Skip that for now. Which carbocation is the most stable? A, B, C, or D? B, that is correct. And why is it the most stable? Tertiary and allylic, resonance stabilized, that's right. A is only tertiary, no resonance stabilization. C is resonance stabilization, but it's secondary. And then, of course, D is a vanillic carbocation, which is unstable. All right, so quick review here. We want to have more bonds and fewer charges, right? So if we look at the resonance structure on the left for acetone, that is the major contributor, and that's how we always draw it, right? The one on the right shows charge separation, and so it's the minor contributor. However, it is the resonance structure that gives the partial positive charge to the carbon of the carbonyl, right? And we learned in chapter 12 with organometallic reagents, that's why organometallics attack the carbon of the carbonyl and not the oxygen of the carbonyl, because that's the carbon that has the partial positive charge, right? Rule number 2, remember, we always want to try to have all of the atoms having an octet, and that's why this is the more stable resonance structure of the major contributor, even though oxygen bears a formal positive charge, because everything here has an octet. Over here, not everything has an octet. So we always want to have all of our second row elements having an octet. And remember that if we have a choice, we want to always place the negative charge or the positive charge on whatever atom can best handle it. So if it's a negative charge, you want to put that negative charge on the most electronegative atom to be your major contributor, more stable resonance structure. If it's a positive charge, you would want to put that positive charge on the least electronegative atom. Okay? But in this case, we're only looking at negative charges in Rule 3 here. Which of these four resonance structures contributes the most to the overall picture of this molecule? So the molecule showing up there in the upper right. What you think? You think D? You meant A? You meant the A? Okay, all right. Why is it A and not D? Ah, there we go. Yes, has to do with the octet rule. That's exactly right. All right, so let's look at some other conjugated systems. We can have a variety of conjugated systems. You can see 1,3-butadiene is a conjugated system. We have that double bond, double bond motif that we've talked about so much. 1,3-pentadiene has the double bond, double bond. It too is conjugated. How about 1-pentene-4-ine? We have double, single, and then multiple, right? It's not conjugated. This is an isolated alkene. This is an isolated alkyne. Pardon? 1-pentene. 2. Oh, well, the alkene, it takes precedent in the naming system. It's okay. 1,4-cyclohexadiene. That is a non-conjugated. These are just two alkenes that exist that are separated because we have double bond, then double bond, right? And down here we have octatriene, double, single, double. This is a conjugated system over carbons 2 all the way through 7. This is one pi system throughout the entire thing, right? And so we have conjugated systems, we have non-conjugated systems shown up there. Yes. Yep. You could have triple, single, triple. Absolutely. Okay. So when we have these situations where we have no conjugation but multiple double bonds or multiple triple bonds or whatever the case may be, we just call them isolated alkenes. In this case, it's an isolated diene because we have two alkenes, right? In 1,3-butadiene, we don't call this it is a diene, but you need to say it's a conjugated diene. This is a stabilized system compared to this one. We can also have cumulines, okay? And we've built models of these before in class. This is an example of a molecule known as allene, or 1,2-propadiene, excuse me. What's the hybridization of the central carbon? It's sp hybridized, right? How are the p orbitals with respect to one another on an sp hybridized carbon atom? Just on the atom. They're orthogonal to one another. That's right, they're 90 degrees. So are those two alkenes communicating with each other? No, they are not conjugated. You've got one pi system in this plane. You've got the other pi system in that plane. And there's 90 degrees between them. They can't overlap. Okay? And so you have no communication of one pi system here versus the pi system shown here in blue. Okay? That's a cumulated system. And cumulines are kind of interesting molecules in and of themselves, but they are not conjugated. Okay. One of the nice things about these dienes, they can exist either in the S-trans or the S-cis form. Okay. Which one, if you were to go to the NMR and look and see, and you can tell the difference between the S-trans and the S-cis in the NMR, which one would you see? You would see the S-trans. That's exactly right. Okay. The amount of S-cis that you have at any given moment is actually quite tiny. Okay. Where do we get the word S? Why do we have to write S-trans or S-cis in these systems? What does the S stand for? Not here. No, this doesn't have to do with R and S configurations. It's the rotation around a what? A sigma bond. That's exactly right. So we're talking about something being trans or cis about a sigma bond or a single bond. Okay? So you have to write S-trans. Remember when we were talking about cis and trans before, we were talking about things in molecules that were geometrically fixed because of like a pi bond, right? So we could have, for example, two chlorines around an alkene that would either be trans to one another or cis to one another, right? There wasn't free rotation around that double bond. And so that's really what trans and cis should be utilized for. But when we're talking about these types of systems, we're talking about cis and trans around a sigma bond. And so we have to denote it as such. Okay? The interconversion is actually quite fast. The equilibrium lies to the left. Okay? Why, Chance, do you think the equilibrium lies way to the left? Why is it that when you go and look at the NMR, all you'll see is the S-trans configuration of the molecule? Okay, can you tell me why? That's exactly right, yeah. So these two, if you actually build a model and draw the hydrogens in, these carbons are as far apart as possible. When I rotate them, these hydrogens are actually pointing towards one another and starting to get in each other's way. And that's why the S-trans is so much more stable than the S-cis. It's all about sterics, things getting in the way. Okay. If we look at a conjugated diene, so let's look at 1,3-butadiene as an example. What we notice, okay, is that we normally say double bond, single bond, double bond. But if we look at the for comparison chart here, is that completely true? If that were true, if it was really a double, single, double, we would expect this to have the bond length pretty close to a single bond, right? But in fact, it has a bond length that is actually quite a bit shorter. And there are two reasons or two explanations for this. Okay? What are they? What do you think the explanations are, Sarah? Why would that single bond be a little shorter than a common carbon-carbon single bond? Okay, we have two different hybridizations. Now explain to me what that means. Why would the hybridization difference make a difference in the bond length? What are the hybridization differences? Okay, that's the second explanation. You're right on track. We'll get to that. Let's think about the hybridization argument. Why should that single bond be shorter than a single bond that's shown up there? What is the hybridization difference between these things that we're comparing? Okay, so we have sp2, sp2 overlap, right? And over here we have sp3, sp3 overlap. Now explain to me why you would expect a difference in the bond length based on hybridization.
It's got more S character, it's a tighter bond.
That's exactly right. So sp2 has more S character than an sp3, right? So the orbital is more protruded or closer to the nucleus? Closer to the nucleus. And so when those orbitals come together and overlap, it's going to result in a shorter bond. The sp3, it's mostly p character, and so the orbital actually extends further out. And when those two orbitals come together to overlap, they'll form a longer bond. Okay? Now, Gabby talked about the fact that we can draw resonance structures between these things, right? And if we draw one of the resonance structures, what happens to carbons 2 and 3? So, Gabby, walk me through it. So we've got 1,3-butadiene. How can I draw a resonance structure for that? Okay, so I can move here like this, right? And in doing so, I put a double bond there. I'm going to put a positive charge there and a negative charge there, right? So what is that telling us about this carbon 2, carbon 3 bond if I look at both? It contains some double bond character, and it contains some single bond character. The hybrid of that would be shorter than a typical single bond, but longer than a typical double bond. And that's exactly what you see. It's about in the middle. So resonance can explain a lot of things that we deal with in terms of orbital theory quite nicely. Okay? So yeah, here's the picture showing the kind of a representative cartoon of the orbital sizes. So you can see that an sp2, if we go from the center of the carbon out, is considerably shorter than for an sp3, and so that's the orbital argument for why that bond is shorter. But we can also explain it with resonance. Okay? Now, we know that things that we can draw resonance structures for are more stable, correct? And you know that because I've told you that, number one. But you can determine this experimentally, okay? And the way that we determine this experimentally is usually to do some type of reaction that's going to give, that's going to be exothermic, that we can measure the heat that's released, right? So if something is really unstable and it releases heat to go to the ground state, or to the more stable state, excuse me, is that going to release a lot of heat or a little heat? If it's really unstable, it's going to release a lot of heat. But if it's more stable, right, and the reaction goes, we're going to release less heat, right? And so we can do this quite easily. We can take 1,4-pentadiene and 1,3-pentadiene. Both of these molecules have the same number of carbons, same number of hydrogens. They are isomers of one another. We can hydrogenate these molecules to where we get pentane in both of them, so they go to the same product, right? So the floor is the same. And we can measure the heat that comes off of these reactions. In this top example, we get 61 kilocalories per mole of heat coming out. This bottom reaction will only get 54 kilocalories per mole of heat coming out. Okay? Why is that? It's because the conjugated system is lower in energy to start with. And so when the reaction occurs, you get less heat. Okay? That's proof that these conjugated systems are, in fact, more stable. Okay? Can you tell me why these reactions are exothermic? Why is it that we get heat released in this particular reaction? Okay. Almost. No, you're close. You said hydrogen bond.
Oh, sorry, covalent bond.
Okay, covalent. Well, a pi bond is a covalent bond.
But single bond better than double. Yeah, single bond
Why?
better than double bonds because rotation.
You guys are right there. Help them out, Katie. What do we have in the product? All what? Sigma bonds, right? And in the starting materials we have pi bonds and sigma bonds, right? So why is a sigma bond stronger than a pi bond? Why is sigma stronger than pi. Going back to 255 here. There you go. That's right. A sigma bond is direct overlap. Good, strong, nice orbital overlap, right? Nice and strong. Pi bond is only touching on the edges. Remember, the p orbitals don't completely overlap. They just touch on the edges, so to speak, right? And so a sigma bond is a stronger bond than a pi bond, right? And so we're sacrificing a weak bond and gaining many stronger bonds, right? Stronger sigma bonds. That's why this reaction will be exothermic. I know before I even go and set this reaction up that it's going to be an exothermic reaction, okay? Because of how the bonds are going. Anytime we go to more sigma bonds, you're going to have an exothermic reaction, okay? So if we look at our conjugated system, we know we can draw 3 resonance structures for this. We can draw charge separated. And actually, there are 2 charge separated resonance structures, right? So which way would Gabby have to push the arrows here to get this one? Which way would you draw the arrows, Brienne, to get this resonance structure? So if I started here, which way would I draw the arrow? This way, right? And that would put the positive charge on this carbon, the negative charge on that carbon, okay? How would I push the arrows here to give me this resonance structure? Just the opposite, right? And so the resonance hybrid shows that between all these carbons I have partial double bond character. And actually I should also draw the partial charges up there as well. Okay. All right, now let's talk about some real chemistry with these systems. Okay? What do you all know that we can do to carbon-carbon double bonds in general? We can do addition chemistry. Well, we can do elimination to get double bonds. You can, but that wouldn't be an elimination just of a double bond itself, okay? You'd have to have some halogens on that. Yeah, you're right, you could do that. But just the conjugated system itself, we can do electrophilic addition. Just like we can do electrophilic addition to a carbon-carbon double bond, we can do electrophilic addition to conjugated carbon-carbon double bonds. However, it's a little more complicated because where the things add can be different. Okay, if it's in a simple double bond, addition always occurs between carbons 1 and 2, right? If we just have a simple alkene. But now if we have a 1,3-butadiene, for example, you can imagine the addition occurring over multiple carbons. And so we're going to have to think about this idea of kinetic versus thermodynamic control of our product. It means you're going to have to pay close attention to the reaction conditions, okay? Temperature is going to be really important here. At really cold temperatures, a particular addition will occur. At higher temperatures, a different addition will occur, okay? We probably won't get to the Diels-Alder reaction today, and so I do have a pen cast in chapter 13 for that you will need to read or view before you come to class on Wednesday for our inverted lecture, okay? So, if we think about an isolated diene, why is this isolated, Jamie?
Because it's not a double.
That's right, I've got a double, single, single, double, right? And if I imagine, and this would be a trick here, but if I could be really, really careful and only add a single equivalent of HBr, I would only add HBr across one of the double bonds, and it would follow Markovnikov's rule, just like we learned, right? The hydrogen would go to the carbon with the most hydrogens, and the bromine would go to the other carbon, right? That's what we would call 1,2 addition. Why do I call it 1,2 addition? Across carbon number 1 and carbon number 2, right? So, follows everything that we've ever talked about before, right? The only trick here would be adding exactly one equivalent. but let's assume we could do it, we would end up with this product. Okay? Nothing new there. What's the intermediate in this reaction? Pardon? Not here. I don't have Br2. What do I have? HBr. So the hydrogen protonates the carbon-carbon double bond, and I end up with a carbocation intermediate, remember? That carbocation then gets attacked by the bromide to give the product. Okay? Nothing new. However, if I'm thinking about a conjugated system, okay? Brienne, why is this a conjugated system? Double, single, double, right? So I've got a conjugated diene, and you come into the lab and you've gotten really good at adding only one equivalent of HBr, and you add one equivalent only of HBr to this system, you would actually find that you have two different products when you go look at the NMR. You'll find that you have the 1,2 addition product where it adds across carbons 1 and 2. But you'll also find that you have a 1,4 addition product where the hydrogen was added to carbon number 1 and the bromine was added to carbon number 4. It's a conjugated system. It's one pi system. And so you can have two different additions, a 1,2 addition product and a 1,4. 1,4 addition is also known as conjugate addition. Okay, you need to know that term. I will use it freely and liberally. When I say conjugate addition, you need to know what we're talking about. We're talking about the addition of something across carbons 1, or atoms 1 and 4. I shouldn't just say carbons, but atoms 1 and 4 in a conjugated system. Okay? Both occur. You will find both. So it seems kind of like a useless reaction, doesn't it? We end up with two products, and maybe we only want the 1,2 addition product. Or maybe Katie wants the 1,4 addition product only. So we need a way in which we can control these reactions, and that's where reaction conditions come into play. Okay? So let's do an experiment. Here's the results. So Karina comes into the lab, and she decides to take the 1,3-butadiene and the 1 equivalent of HBr, and she decides to run this at really cold temperatures. So she goes, she gets a scoop of dry ice, pours it into some acetone, which gets you about a -78, -80 degree bath. She puts her flask in there. She cools everything down. She adds the HBr slowly so that it doesn't warm everything up real quick. And what she finds when she goes to the NMR is that 80% of her mixture is the 1,2 addition product. And only 20% of it is the 1,4 addition product. Well, then Nate comes in, and he decides to do the experiment. And he's out of dry ice. So he figures, well, what the heck, we'll just do it at room temperature, okay? Or a little higher, maybe 40 degrees, whatever the temperature is in the lab. Maybe we're running this in the summer, right? It's kind of hot up here. And he runs the reaction at higher temperature, and lo and behold, he finds exactly the opposite. He finds that the majority of the product is 1,4 addition, and the minority product is the 1,2 addition. Which one of these is under kinetic control, and which one is under thermodynamic control? The lower temperature is the one under kinetic control. So the 1,2 addition product is therefore the kinetic product. What do I mean by that? What do you think I mean by that, Russell? What do I mean by the 1,2 addition product is the kinetic product? What does kinetic mean to you? If something's kinetic, what does that mean? It means fast, right? We're talking about kinetics, we're talking about how fast things go, right? So what does that tell us about the 1,2 addition product?
More affected by how fast things go versus the temperature.
Okay, it's the one that forms fastest. The 1,2 addition product is the one that always forms fastest. Okay? The 1,4 product, therefore, is the thermodynamic product, meaning what? It could mean that it forms slower, but I can actually show you thermodynamic products that form fastest. But what does it mean to be a thermodynamic product? It is affected by temperature, that's true, but what does it mean to be a thermodynamic product? Okay, it's the most stable. The thermodynamic product is the most stable product. The 1,4 product is more stable than the 1,2 product. Delaney, can you tell me why? Why would the 1,2 addition product be less stable than the 1,4 addition product? Okay, the H and the Br are closer together. That's true, but that doesn't explain it. Pardon? Pardon? Why? You're right. It has to do with the double bond. What can you recall from 255 about alkene stability? What kind of alkene is the 1,2 addition product? Okay, we don't call it a primary, but you're right. It is terminal, but it's monosubstituted, right? It's an alkene with only one other alkyl substituent, right? So we would call that a monosubstitute, which is where you were kind of going with the primary, I think. What about this one? It's disubstituted. What do you all remember about the stability of alkenes? The more substituted the alkene, the more stable it is, right? So remember, mono was less stable than di-substituted, less stable than tri, less stable than tetra. Okay? So the 1,4 addition product gives me the more stable alkene, and that's why that product is overall more stable. Okay? Now, let's do another experiment. I don't have the result for this one yet on the slide, but let's suppose Chance comes in and he wants to form the 1,2 addition product. So, being the bright student that he is, he goes, well, I need to do this at minus 80 degrees. I need to add one equivalent of HBr, and I need 1,3-butadiene, right? So he sets up the experiment. He puts dry ice in acetone to create a low temperature bath, puts his flasks in there, puts all the reagents in there. And then his buddy Nate comes in and says, hey, let's go to lunch. And so Chance isn't there to keep adding dry ice. What happens to the temperature of the bath as they're up for lunch? It starts to rise, right? Well, he goes to lunch, he gets distracted and maybe goes to Starbucks, and before you know it, the day's over. He didn't work his reaction up. He comes in the next day. What do you think he'll notice? Will he notice an 80-20 mixture this way? Or will he notice an 80-20 mixture here? The second one. It actually turns out that the kinetic product, given enough time and temperature, will actually rearrange to the more thermodynamically stable product. So it's very, very important that he run the reaction at low temperature, work it up at low temperature, and use it immediately in whatever he wanted to use it for, because on standing it will. Now, it's probably not going to be that fast, okay, as I've described. But the kinetic product always forms first. And then if you're at higher temperature, it can rearrange to the more stable product, okay? So, I just said that, so we'll skip that. So we know that the kinetic product, since it occurs faster, the energy of activation for the kinetic product has to be lower, right? But the thermodynamic product has to have the lower product energy, right? So that's why C is lower than B, okay? Why is it that the energy of activation for the kinetic product is lower? It does, but why? But what about it? What about the reaction makes that have a lower energy of activation? Well, let's think about it. Let's think about it. So HBr, I'm at low temperature. What happens, Harrison? What's the first step in this mechanism? Okay. We do the protonation, right? I've just added the hydrogen. At really low temperature, are things moving fast? Where's that bromide with respect to the carbocation that we just generated? Really close or far away? Really close, right? And so at low temperature, this isn't moving around very fast. It just attacks, and we end up with the 1,2 addition product. Okay? But wait a second. This is a positive charge in conjugation, right? I can draw a resonance structure for this. Right? But at low temperature, the bromine, or the bromide, is further away here, right? That's why the energy of activation is so much lower here, right? This has to actually move to the other side to do the reaction. That takes energy. Energy of activation is going to be higher, right? So at high temperature, what happens? Okay. Quicker? Even at high temperature, isn't the bromide still closer to the carbocation that we just generated? Yes. The answer is simply yes. It's always, your kinetic product always forms first. But what happens is at high temperature, this is allowed to equilibrate. This is a reversible reaction. This can come off and regenerate the carbocation, and it will equilibrate until you form the more thermodynamic product, which is the most stable. Okay? So even though this is the most stable product, we're still going to go through the kinetic product first because it's the lower energy of activation. Okay? If I keep it really, really cold, I can isolate this and use it. But if I warm it up, this will get formed, it will revert, and it will eventually form the more thermodynamically stable product. Okay? So all of these processes are reversible. Don't forget that. Okay? The kinetic product always forms first. Always. Okay? And so this is maybe a little better way of showing it. So yes, this is a resonance delocalized carbocation. The bromide is certainly closer to the carbocation at C2 because it came along for the ride to protonate the carbon-carbon double bond. So its distance to C2, right, is much shorter than its distance to C4. Okay? And so at really low temperatures, it's going to react mostly at C2, and you're going to end up with the kinetic product. You let it warm up, you will get the product where it is added to C4. So in reality, over these conjugated dienes, how are we adding to the double bond? We can add either in a 1,2 fashion or a 1,4 fashion, right? And if we do a 1,2 addition, that's known as the kinetic product. It's also known as simple addition. If we add to 1,4, that's the thermodynamic product, also known as conjugate addition, right? Or 1,4 addition. All right. So let's work a couple of examples from the old exams, ACS exams. We can work together. What's going to happen here? What do those two arrows mean? 2 steps. So we take the starting material, and we're going to add HCl, right? And we're going to take that product, and then we're going to add chlorine. What assumption do I make in this problem? Pardon? Okay. What other assumption do we make? 1-to-1 equivalence. What other assumption do we make? What about temperature? It's at room temperature or higher. Okay? So, what kind of addition am I going to do? Conjugate addition. Very good. So, Gabby comes in. She takes her 1,3-butadiene. She leaves it at room temperature. She adds HCl. How is that going to add across this system? 1,4. And you're going to end up with this, right? Now, Brienne takes her product that Gabby made and now adds chlorine to it. What happens now? It's just going to add across the carbon-carbon double bond, right? And so we end up with which is which one? Very good. Okay. We will watch the pencast on the Diels-Alder reaction. This is a very, very important reaction. If you'll read in your book, you'll see that it could have had a different name. Other people were looking at this, but Diels and Alder were the first to recognize that this type of reaction could be general. This is perhaps the last carbon-carbon bond-forming reaction that you all will really learn. You will know most of the carbon-carbon bond-forming reactions after we study this one. All right. See you all on Wednesday. Oh, wait. Tonight, 6 o'clock in here. Bring your inverted lectures that you want to work on, and we'll go over those. So from 6 to 8 in here. Hope to see you.